Okay, so we did the card sort. We've kind of got a handle on our types of reactions. Everybody did a great job sorting. But we need to spend a little bit more time on double replacement reactions because the double replacement reactions actually have some subcategories. And I've had a couple people ask me, when we're doing these titrations, how exactly are we supposed to know how I'm going to get a balanced chemical equation? And so we're going to deal with that today. For the moment, you don't need your goggles unless you really, really like wearing your goggles. I will let you know at the times that you need to put them on. So we're going to look at some possible double replacement reactions. We're going to do a few on the little piece of paper in front of you, and then turn you loose to work on a lab where you're going to have to use these solutions to sort out the identity of some other solutions. So our double replacement reactions are kind of the double date gone bad reactions. Things like AB plus CD. Everybody goes out to dinner and realizes, oh dear, I have the wrong date. Hey everybody, let's switch. And so C goes with B, and A goes with D, and everybody's happier than they were before. These reactions actually come in three different varieties. There's precipitation reaction, which is, I think, probably the most common one, the one that everybody recognizes the most. Neutralization reaction, which is what we needed for our titrations. And then we have gas-producing reactions, which are the ones that when you put the two drops together, they go fizz-fizz. So a precipitation reaction starts with two soluble ionic compounds. They switch partners, creating another soluble ionic compound and an insoluble ionic compound. Now, when I talk about soluble and insoluble, that has to do with something called the solubility rules. We have let you, up until this point in time, simply assume that all double replacement reactions are going to take place. And that's not quite the truth. If nothing forms out of the swapping of ions, we really just have a double replacement reaction that starts with a bunch of ions and ends with a bunch of ions, and nothing in particular happens. So we'll be back to the solubility rules, but when we talk about soluble and insoluble ionic compounds, some ionic compounds will dissolve in water, sodium chloride, for example. Some ionic compounds will not dissolve in water, rocks, for example. You know very well that when it rains, all the rocks don't dissolve. Rocks are made of ionic compounds, so it must be the case that not everything ionic dissolves. So these will be the rules when the time comes that will help us figure out what's going to dissolve and what's not. So an example of this situation would be if we take potassium iodide, react it with lead nitrate, and we create potassium nitrate, which happens to be aqueous, and lead iodide, which happens to be a solid. And in terms of knowing which of your products are aqueous and which of your products are solid, that's where our solubility rules are going to come in. The next possibility for a double replacement reaction is going to be a neutralization reaction. This is like what we did when we were titrating. We took an acid and a base, and you're going to recognize your acids because they contain hydrogen ions somewhere in their formula. And you're going to recognize your bases because they contain hydroxide ions somewhere in the formula. And in the course of a neutralization reaction, the hydrogen ion from the acid and the hydroxide ion from the base get together to make HOH, which we more commonly write as H2O. So it's really exactly what it sounds like, an acid and a base making what we think of as a neutral compound, which is water. So this could be something like you did in lab. H2SO4 reacted with two sodium hydroxides, and made Na2SO4. So there's your ionic compound. And the water. And in the process of this reaction, we took something that was acidic and something that was basic and ended up with a mixture that was neutral. The next possibility is a gas-producing reaction. This is a reaction that fizzes, and the fizz actually comes from a two-step process. The first part of the process is just kind of your classic double replacement. So we take an acid, maybe we'll do nitric acid, and it has to react with either a metal carbonate or a metal hydrogen carbonate. So we'll use sodium carbonate. And we have a double replacement reaction where the hydrogen gets with the carbonate and the sodium gets with the nitrate. And so we end up with H2CO3 aqueous plus NaNO3 aqueous. We balance it. And at first it looks like nothing's really going to happen here. We start with a couple of aqueous compounds, we finish with a couple of aqueous compounds, and it looks like nothing's going to happen. But there's a secondary reaction that occurs because of the presence of this stuff. This stuff right here is carbonic acid. It's the stuff that makes soda fizz. At very high pressures, like inside an unopened soda bottle, the carbonic acid stays as carbonic acid, it stays dissolved, and nothing really happens. But at atmospheric normal pressures, carbonic acid actually isn't stable, and the carbonic acid undergoes a decomposition reaction, H2CO3 aqueous, where it falls apart and it makes carbon dioxide and some liquid water. And that's what happens when you crack open a bottle of soda and all of a sudden all the bubbles appear on the side of the container. It's because carbonic acid decomposes at normal atmospheric pressures, and when it decomposes, that's where we get the fizzy stuff that makes soda have its appealing little bubbliness. Overall, if we were to look at this process, and what we'd do is we would basically take this H2CO3 and replace it with the CO2 and the water. So our overall reaction here would be an acid, 2HNO3 aqueous, reacted with a metal carbonate, we used sodium carbonate, and produced the carbon dioxide and the water. And so that's the part that came from the carbonic acid. And 2 aqueous NaNO3s. So those are our three possibilities for double replacement reactions. And we're going to take each of these reaction types and look a little bit more closely at it. But as we do that, we're going to actually do each of these reactions. Someplace on your desk where it's not going to be in the way and where it can lay flat, I want you to lay out your reaction surface. And then put the plastic over the top of it. Obviously, we cannot put drops of liquid on paper and not have that cause a problem. And then we're going to do each one of these reactions, looking at each of them individually as we go. So grab your sodium chloride or your aluminum chloride reaction dropper out of your thing, and I want you to put a drop of that stuff half on the white half on the black. So just put one little drop on the reaction surface. And then I want you to take your AgNO3 dropper, and without touching the droplet that's already there, because I don't want you to accidentally pull the droplet that's already there back up into the dropper, drop the AgNO3 right on top of that. And what you will notice is that it turns white. Okay? We get kind of some white cloudiness out of this whole thing. The reason I'm going to have you do all your reactions half on the white and half on the dark is because if you do them half on each place, if something happens that makes it turn dark, you'll see it against the light background, and if something happens that makes it turn white, you'll see it against that dark background. So now we're going to describe what happened. That white stuff that you just made is what we call a precipitate. Okay, so that's why we call this a precipitation reaction. So we just took aluminum chloride and reacted it with silver nitrate. If we go back to our old chem study skills, when we predict the products of double replacement reactions, the first thing we do is we think about what ions are present. Not so much how many, just which ones were there. So we take each compound, we break it down into its ions. Now, we trade partners, and we write chemical formulas paying attention to these charges. Aluminum is 3 plus, nitrate is 1 negative, Al, NO3, 3, plus, Ag is 1 positive, Cl is 1 minus, and then we've learned that we have to balance the equation. And in your first chemistry class, we let you just stop there. We said, don't worry about the physical states on these. We don't have any particular way to know those at this point in time. But now we do. The solubility rules are going to tell us whether our products are solid or aqueous. Here's kind of some definitions. Soluble, that means it will dissolve. It'll get the physical state of aqueous. You're not going to see a precipitate. Slightly soluble means a little bit dissolves. Most will not. We're going to give it a physical state of solid because we are going to see some precipitate. Maybe not a lot, but more like a wispiness than a dark white. Insoluble means that none, or at least an insignificant quantity, is going to dissolve. We're going to give it the physical state of solid. A precipitate forms, and you're probably going to have lots of it. I've got the solubility rules done up in a couple of different ways. On the front side of the sheet, I've got them kind of in a hierarchy. If you want to use the front side of the sheet, you're just going to start at the top, and you're going to work your way down until you find the first rule that applies. So, like rule number 1, all acids are soluble. You're going to recognize an acid because it will start with hydrogen or end COOH. Now, we know that someplace in our reaction, we've managed to form a precipitate. We just have to figure out which of the two things is a precipitate. So we're chasing down aluminum nitrate or silver chloride. So, not an acid. Number 2, all salts. Salt is just another word for ionic compound, so you could just read it as ionic compound. All ionic compounds of alkali metals. Okay, so now we have to think about what's an alkali metal, but we don't have to think very hard because it says right down here at the bottom of the first column, alkali. Okay, good, so we don't have to remember that. All salts of alkali metals and ammonium ions are soluble. That does not seem to apply to our situation. Rule 3, all salts containing acetate, hydrogen carbonate, nitrate, and chlorate are soluble. Okay, this applies. One of my compounds contains the nitrate ion. This one's aqueous. And I don't have to worry about that one anymore. As soon as you find a rule that applies to a particular compound, you mark it as solid or aqueous, and you move on. But we still have to deal with the silver chloride. All salts containing fluoride. All salts containing chloride. Ooh, that sounds like something we're interested in. Are soluble except with silver. Aha, found it. There's my solid. Okay. And so you use this side of the sheet just as kind of a hierarchy. Work from the top down. Here's an alternative way of looking at it. Here they're sorted into things that are always soluble, with exceptions, but there are none because it says always. Things that are often soluble, with some exceptions, and things that are insoluble, with some exceptions. You may use whatever side of this sheet is easier for you to think about. I think I kind of prefer the front, but I think only because that's the way I ran into these first. It was later in life when I saw them done this way. You will not have to memorize all these solubility rules. Right now, you just need to know how to use the sheet. As test time gets closer, we'll talk about which ones you have to have memorized. There are 2 or 3 big ones that you need to know, and by the time we make the list of which ones you need to know, you're going to find out you actually already know those because they're the most common solubility rules and they come up more commonly than anything else. So for now, you can build a complete dependence on using your solubility rule sheet. We just need to understand how that works. So that's our new thing, one of the new things that we're going to do. We can now get a physical state on here. What we just created is something that is called the full molecular equation. We've never given a name to it before because we haven't had alternatives. It's just been the equation. But there are things we can do and places we can go from here. This isn't really a very good description of what happened. Your first little dropper that contained aluminum chloride didn't really contain any aluminum chloride. It contained aluminum ions and 3 chloride ions. That's what it means to be an aqueous ionic compound. It means the compound fell apart into its ions. And if you think back to your previous chemistry class, we used a light bulb to prove to you that when an ionic compound dissolves, it forms ions, it's able to conduct electricity. So that first dropper really contained aluminum ions, and for every aluminum ion, 3 chloride ions. Your silver nitrate dropper contained silver ions and nitrate ions, but in our balanced equation, there's 3 of them, 3Ag plus, and 3NO3 minus. So what we really combined was 4 different ions when you did the drip drip and put them on the piece of paper. When the reaction occurred, we made aqueous aluminum nitrate, which is still aluminum ions and 3 nitrate ions. But then we made that white stuff. That white stuff is solid silver chloride, and the reason we can see it is that the silver ions stuck tightly to the chloride ions and essentially undissolved or precipitated. So the solid stuff was no longer coming apart into ions. This green equation I have written is called the full ionic equation. Now, there are definitely some redundancies in here. There are some things that showed up but didn't do anything. Like, here's an aluminum ion And here's an aluminum ion. The aluminum ion was completely unchanged in this process. The 3 chloride ions, however, stuck to the silver ions, and the 3 silver ions stuck to the chloride ions. But the 3 nitrate ions are still the same when we get to the other side, so we're going to get rid of those as well. And then we're going to create what's called the net ionic equation. The net ionic equation is the business end of what occurred. 3 chloride ions reacted with 3 silver ions to make 3 silver chlorides, or a more reduced form of that says that chloride ions react with silver ions to make silver chloride. And these characters who showed up for the game but didn't do anything are called spectators, because those are the people that show up for the game and don't do anything. Yeah?
The screen share is like loading.
It's what?
Like loading, like it's just a blank screen.
I probably can't fix that. It's probably a networking issue. Was it working before?
Yeah.
Yeah. It's definitely a network issue. Every now and then it kind of blinks out on us. Hopefully it'll come back. Okay, then our spectator ions are the guys that got crossed out. Aluminum showed up for the game and didn't do anything. And nitrate showed up for the game and didn't do anything. Okay, that's a precipitation reaction. So let's try the next little box. So the next little box says, take a drop of aluminum chloride and react it with a drop of copper 2 sulfate. Oh. They're really both the net ionic equation. This one is the better version of it once it's reduced. I would accept either one of them. Yeah. Okay, so drop the aluminum chloride and the copper 2 sulfate together. Yeah, very anticlimactic definitely describes the situation. We took something that was blue, we added a drop of something that was clear, and the whole thing became slightly more pale blue. Not really a super duper spectacular experience here. Let's see if we can fix Guardian. Let me try this. That put us back in business for the screen share? All right. Who knows what its issue was? Okay. So if we do the reaction here, we have aluminum ions and chloride ions reacting with copper 2 ions and sulfate ions. We pull the partner switching. We have Al2 SO4 and CuCl2. It's going to take a 2 here and a 3 here, and a 3 here. And then we go to our solubility rules. So we're looking for aluminum sulfate and copper 2 chloride. Okay. Acid, no. Alkali metal, no. Acetate, hydrogen carbonate, nitrate, chlorate, no. Fluoride, no. Chlorine, aha. All salts of chlorine are soluble. This time we don't have one of the 3 exceptions. So this accounts for the copper 2 chloride. Okay, keep going. Rule 6. Most salts containing sulfate are soluble. We have a sulfate, except silver, barium, mercury, lead, and strontium. No exceptions. This is aqueous. This explains why we didn't see anything when we put it together. If we set out to write the full ionic equation by breaking up everything that's aqueous, we get 2 Al3 positive. 2 times 3 is 6 Cl negative. 3 Cu2 positive. 3 SO4 2 negative. Becomes 2 Al3 positive. There's nothing down there. 3 SO4 2 negative. 3 Cu2 positive. And 6 Cl minuses. And we cross off everything that's the same on both sides. 2 aluminum ions, 2 aluminum ions. 6 chloride ions, 6 chloride ions. 3 coppers, 3 coppers, 3 sulfates, 3 sulfates. Nobody did anything. No reaction. And often we're just going to write NR. Now, once you get to the point of proving that they're both aqueous when you're writing a chemical reaction, you're actually done. You don't need to go through the process of writing all of these and crossing them all out. I just wanted to show you why it is that sometimes there's no reaction. The reason that sometimes there's no reaction is that when everything falls apart into its ions, you end up crossing off everything, and that's why nothing happens. So there's our precipitation reaction. Okay, for the next one, I actually do need you to put your goggles on. So I want you to do the sodium hydroxide with the nitric acid. Okay, now as long as we've got the goggles on and we're in motion here, let's go ahead and do this one as well. So go ahead and do the HCl with the sodium carbonate. Yep, go ahead and do the sodium carbonate and the hydrochloric acid, as long as we've got the goggles on. All right. That second one I expect that you would see some fizz. It probably looks like a little dribble of 7-Up sitting on your table. So these represent, first of all, our neutralization reaction, which was quite boring, and then our gas-forming reaction, which got a little bit fizzy. But they're all technically double replacement, so we can follow exactly the same pattern. H plus, NO3 minus, Na plus, OH minus. Trade the partners. Hydrogen ion gets together with hydroxide ion to make HOH. And sodium ion gets together with nitrate to make NaNO3. And it probably makes more sense in terms of recognition to then cross this guy off and say, actually, that's H2O. And we know the physical state on water while it's sitting on your table. We're pretty confident it neither froze nor boiled, so it's safe to say that the water is in its liquid form. Then we just have to deal with the sodium nitrate. So we go to our solubility rules. Right there, rule number 3, nitrates are soluble, or even before that, sodium's an alkali metal. So that's definitely going to be soluble. And that's why there was nothing to see. The thing that formed was water in the presence of water, so we couldn't see it happen, and then an aqueous ionic compound. This one, as is already balanced, so we don't have any balancing work to do. So we'll write our full ionic equation. H plus NO3 minus Na plus and OH minus. So everything that's aqueous breaks up. Anything that's not aqueous stays together. H2O liquid, Na plus, NO3 minus. Get rid of the things that are the same on both sides. There's our nitrate ions and our sodium ions. And our net ionic equation is an acid reacting with a base to make water. That's our neutralization process. And our spectator ions are the ones we crossed out. So our spectators were our nitrate and our sodium ions. Neutralization reactions are the things that are one of the varieties of things we can use for titrating. When we use phenolphthalein for our indicator, we have to be doing a neutralization reaction because our phenolphthalein measures the end point of that reaction. But when we are going to use these reactions to try to identify things, we're not going to see this one happen. So it's going to happen, but there's not going to be anything to look at to tell us that something happened. So that's something you want to be kind of cautious of as we move forward with this challenge lab, is that while a neutralization reaction will happen, you're not going to be able to visually see the neutralization reaction happen. And then our last variety was our gas-forming reaction. This is the one that looked a little like 7-Up on the reaction surface. We took hydrochloric acid, which consists of hydrogen ions and chloride ions. We reacted it with sodium carbonate, which consists of sodium ions and carbonate ions. Switch your partners. So we get H2CO3 and NaCl. Excuse me. Excuse me again. And I got a little ahead of myself here. I dropped the aqueous in place because the H2CO3 starts with hydrogen. So that's rule number 1. All acids are soluble. Sodium chloride falls underneath rule 2. Salts of alkali metals are soluble. And on paper, at first glance, it looks like nothing's going to happen. But then we remember that carbonic acid isn't stable at atmospheric pressure. So right after this formed, it fell apart and formed carbon dioxide and water. And that's where you got the fizzing. So our full ionic equation here is that 2H positive ions reacted with 2 Cl minus ions to make 2 Na positive ions and a carbonate ion. And then because carbon dioxide is a gas, we leave that together. Water is a liquid. We leave that together. 2 sodium ions. 2 chloride ions. Get rid of everything that's the same on both sides. And my net ionic equation ends up being 2 hydrogen ions react with a carbonate ion to form carbon dioxide and water with spectator ions of chloride and sodium. So that lands us ready to start your double replacement challenge. And we won't get anywhere close to done today, but we're going to put in about 20 minutes of work on this just to kind of get you the feel for what needs to happen, and then we'll come back to this next time. So today you're going to work just with part 1. In addition to the droppers that you have that are marked, you're also going to pick up a little cup that has droppers 1 through 4 in it. And you're going to take the contents of droppers 1 through 4 and react them with everything that's in your rack. When I loaded up the rack of chemicals, if I did a good job, these are actually in order coming right across the front. If you put your racks, like if you get them both turned the right direction and set them side by side, with any luck, these are in order coming across the top, although you might want to just confirm that, but I tried to put them in order for you. You're going to react each of the 4 droppers with all of the things. You're going to create some kind of data table in order to record information